Yeah, welcome everyone to this workshop. I hope that it was easy for you to log into here. I want to talk a little bit first before we get started about who we are. So we are called OSIM. We're a group of people who work in medicine and care about open science. So OSIM stands for Open Science Initiative in Medicine, and it developed out of the LMU Open Science Center. So then, without further ado, I would like to welcome our star guest, our keynote speaker of the day. I'm very excited to have the honor of introducing Ewout. So Ewout W. Steyerberg is a professor of clinical biostatistics and medical decision-making at Leiden University Medical Center and a professor of medical decision-making at Erasmus Medical Center in Rotterdam. He has been chair of the Department of Biomedical Data Sciences at Leiden University Medical Center since 2017. He has interest in a wide range of statistical methods for medical research, but is mainly known for his seminal work on prediction modeling. I met Ewout at a pharmaceutical statistics workshop in Boston, and from that workshop, I know that he's not only a brilliant statistician, whose work has influenced mine several times, but he's also a great speaker and an enjoyable person to have a drink with. Ewout, Ewout is so famous, he has even a Wikipedia page. From there you can read that Ewout has a family with 3 children and a dog called Bass. And that Ewout is a runner. Just like marathons, science is a combination of training, good planning, endurance, and a bit of luck. With this, I would like to hand over to Ewout, and I'm excited to hear about his perspective on science and open science in particular. Ewout, the floor is yours.
Thank you so much, Heidi. This is one of the greatest introductions I have ever enjoyed, so thank you for that. And yes, I remember our meeting in Boston, which was really nice. And I also thought about that because of some link with the open science issue. I think the question you asked me was rather critical. It was about comparability. It was about how can you compare 2 patients. And I think that is a key issue that comes up in many scientific debates and also is really central to the whole field of epidemiology. Comparability. You want to compare treatment, you want to compare prognosis, you want to compare outcomes. That is a comparability issue, and that's also actually a theme that I like to address in this lecture. And there's one idea that more and more data will help us. That's a bit also in the open science culture. But then, yes, can you just combine data from any source? Or so that is a link with our meeting in Boston and your first question, which was really to the point, of course. So thank you. And also it's funny about the wiki page that some students made that for me, and I was a bit overwhelmed and should I delete a wiki page, but there's also an open science element to it, that I had a picture of my profile, which I thought was relatively open. We had that we bought that as a department, I think, or so, when we have pictures of department people. But it was removed from the wiki page, and I got a warning message that I should not post material that was not really open. So that is a link with the open science movement. But without further ado, I will start with sharing my screen, I think. I see Mr. or Mrs. She in the picture now, but let me just start a share screen, and that is my presentation for today. So of course, before starting, I should also thank the organizers for inviting me. I think it's a really great initiative to have this online meeting, this seminar. I think it was originally planned to have it in person, right, Heidi and others?
Yes.
But now we can do this online, and there are many excellent examples of these kind of webinars. So you will monitor questions that come up, etc., and I will just present. It's a bit strange to be talking to a screen, but we have all been doing this for the past month, I think, 3 months or so. Anyway, so I'll talk about open science for research questions. Can we address bigger questions now because we are more collaborative or so? What about the issues in data sharing, privacy issues, how do we deal there, and then analyses and interpretation. And I was inspired by many people around me, but also specifically here, there's a prostate cancer consortium, GAP3, that I like to mention, and also the Center TBI study. That's a study in TBI, traumatic brain injury, where I'll also show some results from. And this picture is the Leiden University Hospital, when there were still many people walking outside. Let's see. Yeah. So I checked out your website and material, of course. So this is what was sent around, right? The program. So there's very interesting material to go through, as Heidi, as you also indicated. It's really important. I think are really key issues in open science that are addressed in the lectures. It's really also quite didactic, giving hints and tips to researchers on how to deal with various issues, to understand what is happening. So maybe later we will go in more detail about these issues, like publication bias, p-hacking, and these nice terms, and what we can do about that. So this is what was sent around. I also checked out what can I find for the Netherlands. Well, there is an Open Science Initiative.nl. So this is Dutch National Program, Open Science, and the elements I think are largely overlapping. So it's about publications, open access issues, about research data. This is an organization that manages sharing data, that archiving data, that sort of thing. Authorship issues relates to publications, I think, but this is mentioned here separately. And open source software. I think that was a specific issue, Heidi, that you addressed also in your lecture, and I fully agree with that. It's really a major development that we have seen over the past years and will continue, I guess. There was also an announcement of an Open Science Festival, and that's actually interesting. So it has a save the date, but yes, unfortunately, it will not take place in 2020 August. We are in the process of rescheduling, and that's maybe also kind of a general feeling that you get sometimes, that I get with this open science. Like, say, it has a lot of promise, but what's really happening now? Well, it's a gradual thing, and here this is a kind of a joke that is postponed a bit, but it will take place. And finally, I'd like to mention, and we'll come back to that maybe in the discussion, there's an initiative, Coalition S, which is quite strong, sponsored by funders of research in the Netherlands. And they have this Plan S, so Coalition S and Plan S, and they argue for open access publication and movement of journals in that direction, beyond what we have currently, that I have been doing, like paying extra fees for open access, that the whole journal should really move in that direction. So this is what is happening in the Netherlands. Well, if I think about open versus something else, I would think, well, that's maybe then against closed science and more confined. We have this. I have this image. I've read many books on history of science. It's also very, very fascinating. But long ago, if we go back in European history, then science was more an elitarian process. Was more for the happy few. Scientists who could afford doing research, right? They had a lot of money or other sources of living, and science was kind of an extra thing. So they did their experiments at a relatively small scale and privately. And the discussion was also not in a really broad community, but small, right? It was these societies and that came up. Some very famous. So here's a picture that I found. It's Blaise Pascal, who illustrates how a barometer works for the pressure. And it's only two people watching, and he showed, yeah, this is how it works. He did a small experiment. He sent people into the mountains to check the air pressure there, etc. That's what you can read on the internet. So relatively small scale, close science. Now, so what is then what I've grown up with in recent times? Science is a profession. You can choose to become a scientist. You get paid for that. And then, yeah, things happen like that are human if you are in a relatively competitive setting. So people protect their data. It's kind of their gold mine sometimes, especially in epidemiology. And they also may protect their code as intellectual property. So you can do things that others cannot. And also there's this tendency to aim for shocking or surprising findings and publish them in high impact factor journals. Go for the top, because that benefits your career. That is then rewarded in this system. So that is a reflection on open science versus more historic, closed, or more recent scientific tradition. And just one example for illustration, because it's so recent, and I read this on Twitter. That's also a more recent development. Go on Twitter, and Heidi, I noted you also posted this this webinar there. So the SurgiSphere scandal. So data that were published in top journals, reports were published based on data that were probably falsified still. And if you go to the people involved, so here is this is well spelled out on Twitter and the internet, and people publish under their name, so they are easy to identify. But I want to highlight this point. So this is a big player in this scandal. He has a history of big aspirations and sorry, I cannot pronounce that, entrepreneurial ventures. So he wanted to really be successful as a scientist and as a businessman, and with a clinical training. The presence in space, so it's really ambitious. And there's another person involved who was apparently a well-respected researcher, was the first author of both retracted papers, and he said, well, he at least made an apology. And he failed to ensure that the data source was appropriate for this use. So he thought these data were real and analyses were real from it. But just to illustrate what can happen, and this is also addressed in the lectures, that fraud and misconduct, they can happen, but it's relatively a small proportion of all the issues that we face as problems in the scientific world nowadays. But nevertheless, it happens, and this is a recent case. I think the overall claim that I would like to start with is open science will make research better. And that's the whole idea, I think, behind it. It's a no-brainer to many. So I noted with the participants, people can vote. So we could make this a vote, but I would guess that the far majority would be would favor this statement. Right? And so my talk is a bit like, okay, I also agree with that. That's why I put it forward. But let's see what are really the strong points. Where can we make research better relatively easily? But what's the practical steps we can take? Some strong points, but there are also some challenges. And that is, I think, also important to not forget about. And I reflect on that based on really, I'm old now, so on my research history, mainly in clinical epidemiology, biostatistics, focused on prediction research and decision making. So I'm a rather practical person. So I checked for my first publication is in '92, and that was in radiology, so on database issues. Then something on prognosis in '93, so that's 27 years ago then. And here's a decision making paper on who to do surgery on. So that's the kind of things I've been involved in. Okay, so let's start in this idea. I have 3 topics about the research questions, data and analyses. Research questions, can we better address big research questions? And one case I like to highlight, which I like very much, is this example that was in the news, I think 2 years ago, was published in 2018, the red card in soccer for dark skin soccer players. So for dark skin players, it's an open archive accessible journal publication, so that's nice. Title, Many Analysts, One Data Set, and how variations in analytics choices affect results, with many authors listed, all that really made a substantial contribution, I guess. So that is an interesting study, I find, because it has this challenge of saying, okay, one data set and 29 teams address a research question, as highlighted here, whether soccer referees are more likely to give red cards to dark skin toned players than light skin toned players. So is there something going on that we would reject ethically, of course, in soccer play. And then the results are that the odds ratios are really all over, below 1, so saying less red cards are given, to 2.9, so nearly 3 times as many red cards are given. Now, of course, this comparability issue comes up. And let me just show you first the results further from how do you go there. Well, these are the estimated odds ratios, 29 teams. So I counted the rows. This is indeed 29 in total. Some are numbered with higher numbers, some dropped out. And the analytical approaches, well, sound very scientific to me. I mean, I'm impressed if someone tells me, I used a zero inflated Poisson regression, not a standard Poisson regression, but a zero inflated. But then another one would say, well, I do just Poisson regression here at the lower end. So when you check for Poisson, which is a standard regression technique, which in this case, relatively rare events, these red cards over large denominator, as a statistician, you might think, well, Poisson regression, not that bad. But the results are very different. You see, so this is an estimate of 0.9, the lowest, below 1. And here there's a very uncertain estimate, but around 3. So this is really puzzling. And if I go on for my favorite technique, I grew up, say, with logistic regression. Binary outcomes are often modeled with that in epidemiology. So let's see where logistic regression is. It's again all over the place. So it's not sufficient to just say I did this, and they have nice names, clustered robust. Robust makes it also convincing, maybe. And generalized linear, it's all, yeah, logit link. Sounds scientific. So why are these differences? And they hint at that here there are unique combinations of covariates. So the comparability issue, how do you compare like with like? How do you compare a soccer player, that the only thing that differs is their color, the color of their skin? And that is, of course, a very challenging issue. And that I think that is the main issue, not whether you did Poisson or logistic. That is not the main issue. But their overall conclusion is that the variation in analyses of complex data may be difficult, even by experts, because these teams, they were not novices or so in their methods. So this is one example to start with on a big research question addressed in a kind of open way. And let me go, there's one, I like to have some, say, modest jokes. So the irony here that I found out is that there is a corrigendum, and it is on this issue of openness that they forgot to add a citation to a Nature commentary, and the authors here, they state they regret the oversight. So in this openness, you need to be really clear also for what you published before. If you presented an online letter or so, yes, you need to mention that in your publication, of course. Okay, so now let me move on to the issue 2 after the red card example. So this is another really big topic about machine learning against more conventional modeling. So this is a case study in prediction of mortality in coronary artery disease, so cardiovascular disease example. This is a PLOS One. This is just it's an open access journal, actually. How does this end up in the media? AI, artificial intelligence, beats doctors at predicting heart disease. And that's really the quote that was in many outlets. So AI beats doctors. So, okay. Question is that, were the findings really convincing in that paper? Was that statement, was that based on the paper? And more general, this question on machine learning versus conventional modeling, is that a systematic issue that we can do better? Many people would hope so. Or is it more like, okay, it depends? Now, let's first look at the paper, the findings. So these are the findings, and I would simply say they're not convincing. So here is a graphic with the key results. There's Cox regression model, a standard technique for survival analysis. Cox is here in this green bar, Cox proportional hazards. And they do that with 30 expert selected variables, well, in different variants, and the best they can get is variant 4, and the C statistic here, a concordance measure, quality of the model is 0.793. Okay, now they say, okay, let's go for something what some might call AI, but it's machine learning, I would say, a random forest technique, developed as an improvement over more classical tree-based methods. Random forest number 7, it uses 600 then, that's this bar, because if you use only 30, it would be worse than Cox. So if you use the same number of variables, you would not do that good. But here, 600, you get to a 0.797. So it's slightly better, it's a third decimal. And the top is the last column here. I cannot see that myself. Let me just do that like this. Number 9 is again with 600 elastic net, which I would simply call a variant of the Cox model, a variant of classic regression, but that does, again, slightly better, 0.801. So yes, there is some ordering, but I would just round all this to around 0.8, right? And so the findings are really not convincing that AI, the random forest, or the elastic net was better. And actually, the authors themselves, they agree with that, I think. So let me go back to that in a second. So they say, we found that random forest did not outperform Cox models. So they do not claim that AI is better than the classical techniques. And also, in elastic net, they rightly say, well, this regularization, so this penalty term that is in the model, in technical sense, L1, L2 penalties, and blah, blah, that is what helps a little bit. So now let me try to go back to this one, because that's not the issue that they showed, and was important, I think, that not only looking at this C statistic, this concordance, this quality measure for discrimination, they also looked at calibration, and there was a disadvantage for random forests. And that's something that I've seen more often, but that's relatively detailed. Okay, so this is what I had on the case study. Findings are really not that convincing, I would say. Now let's see whether this comparison, what are the more systematic aspects of that, and I have 2 examples of that. So one is by Anne-Laure Boelestijs, who is not in the call, I think, but she had presented a very nice presentation also for this session. And she has written.
She is here.
She's here, excellent. She'll want to comment later on, of course, because it's her piece, and I have some more. So this is on this issue on how can we know that one approach is better than another, how we can make fair comparisons. So the comment is that many people compare methods, but usually in a context that they have developed one method themselves. So this letter says, well, we should have neutral comparison studies. And these are defined that they do not aim to demonstrate superiority of a particular method. And they are not set up to show superiority. They're really more neutral in their position. So I like that very much. And I think it's very important to really have this kind of position, and that fits with the open science movement, I think. So this is what she argued, and then she also applied that in practice in a study here that was in 2018 in an open access journal in BMC on random forests versus logistic regression, large-scale benchmark experiment. So this is really big, 243 real data sets. So also this is again an example what we can do in the open science community in this movement. There apparently is a open machine learning, I guess, database, which has many more databases, and over 200 were suited were found suitable to use in this study. Well, the findings were that the random forests perform better. The mean difference in terms of this C statistic, or the area under the ROC curve, that is the C statistic equivalent, was around 0.04. So that's actually bigger than I would have expected, but this was just a finding, very systematic, and yeah, in a neutral comparison. The authors also comment that the results were dependent on the inclusion criteria, so the specific setting of the study, the number of covariates, the sample size, that sort of thing, to use the example data sets. So I have one small comment which I'm still struggling with myself, but the study was done with a cross-validation procedure, so tenfold. So 1/10 was left out repetitively, and that whole thing was repeated 10 times. So that's for stability, 10 times tenfold. And I'm not really sure whether that is sufficient to especially random forest may be a bit unstable, whether you would see that sufficiently with this procedure. But as such, I think this is just the overall finding, and it was at least done in a very transparent and very neutral way. I agree with that. So there is maybe then this clarification. So when is machine learning better? When do they work best? When does this random forest work best? And at least what we know from other research is that the sample size needs to be large. So we labeled that here, also in BMC journal, that modern modeling techniques are data hungry. So data hungriness, that is an aspect in modern methods in machine learning, AI type of developments that we illustrated in this study. So that is also in line with open science, that yes, we can have access to larger data sets. So that would bring modern modeling techniques make that more a reality, would be in to the advance of modern techniques, because sample size is really a requirement and a limitation of much of the current research. So more clarification may be needed, but this systematic comparison, as I showed, at least suggests that it may have an advantage. The studies that were done before on the same topic were in a systematic review. So here we did a review of machine learning versus more classic modeling, and it has this Journal of Clinical Epidemiology title, an explanatory title. A systematic review shows no performance benefit. No benefit. So we had a negative conclusion reviewing previous studies. And if you see that in the media, well, on Twitter at least, they say, well, this paper on logistic regression is equivalent to machine learning, has generated many reactions. I think there were 100 Twitter responses or so. It may be misinterpreted, and well, I like this comment actually, because it's true that we did not look at seminal contribution of deep learning to image analysis. No, we did. There was not a comparison there, because image analysis there is really, I think, convincing demonstration of deep learning being really beneficial there. So that was lacking from our comparison. But if you look at what we did find, so we did look at differences in discrimination. Here is a forest plot of that. So overall, any machine learning versus logistic regression, logistic regression, the difference was to the advance of machine learning, 0.25 on a logit scale, but well, so at least it was higher. Also confidence interval around it in 282 comparisons. So really a large number of studies was reviewed. And then we detailed that by specific techniques. Trees or random forest are here again. Random forest seem to do really well here. But then we separated that in low risk of bias versus high risk. Well, this is of course this is tricky. How do you define low risk? But that was what we called a fair comparison, going to this neutral position. So things like refitting the machine learning algorithm on the training on the validation set. That was not. That was then high risk of bias, or other, say, tuning tricks in the validation of this of a machine learning model. So in this question, when we did this selection, then the difference was really actually absent. I noted later that random forests still are a little bit on the positive side, but that's a relatively small number of studies, not so clear from this review. But the key point was that, yes, if you really are careful in selecting from the literature, then there may not be that much of an advantage of these modern techniques. That is the other comparison, so a more classical approach, a meta-analysis, a literature review. So the examples that I showed on these big research questions, I think, is this red card example. That was one data set, multiple modelers, multiple teams. And the second set was more on this, so if there are multiple modeling options, there is the neutral comparison paper with the 243 databases, which showed some advantage of random forests. And there's a review of these 282 comparative studies in a kind of meta-analysis, meta-research project. So I thought, Heidi, if you are okay, we might check whether there are any clarifying questions or immediate comments. before I move on to these data and analyses issues?
Yeah, absolutely. So please feel free to ask any questions by unmuting or just write questions in the chat now if you have any so far.
Let's see.
So far, there's one comment by Valentin Riedel who says similar approach recently published for the neuroimaging community here, variability in the analysis of a single neuroimaging dataset by many teams.
Oh, nice. Yeah. Yeah, that's in line with the first red card paper, I think, right?
Then there's one question that says, are methods really important?
Yeah, well, that's an excellent question. The more as a methodologist, I actually think that there are other things that are at least as important. So starting with a research question and the data. And if there are issues there that you don't have a clear question or a question that cannot be answered with the data, then yes, of course, we have a serious problem that no method, I think, can solve. And for the data, yes, if the data quality is poor, so some big data projects I get involved in, like using data from general practices, they have many missingness. The design is unclear, how people come in, how they drop out. That kind of things are more important than the methods, I think. Sorry.
And there's a follow-up. I think the story is most important point of publication. By the way, I'm a method developer, mostly working with doctors, and I have learned the hard way that methods are overrated. There's another question by Ulrich. The comparison of AUC is a first step. What about calibration?
Yeah. No, so I was happy that the +1 paper on big database analysis, that they showed the problems with calibration. So calibration, if you in the prediction field, you predict a certain give a certain probability, you predict an event, say 10%, and 10 out of 100 should have that event. That's the calibration property. That's often ignored. So I agree that it's important to also consider that. And
then Anne-Laure has a comment. Maybe Anne-Laure, do you want to unmute and say it yourself?
Please feel free to comment, because you have really been into this.
Yeah, thank you very much for mentioning my studies. I just have a short comment on the benchmarking study on the comparison of RF and LR. Basically, as I wrote in the chat, this study included a very, very large number of very different data sets. So it was not focused on, let's say, clinical prediction for patients. I guess that if we had focused on patient outcomes, which is typically the case you are considering more in your own research, I guess that LR might have been better or even much better. And I think that's actually something that we talked about in the paper. The inclusion criteria one considers for such benchmarking studies are obviously very, very important. And somehow we have to make a compromise. We cannot consider too many inclusion criteria and focus on too small subgroups. Otherwise, we cannot do inference anymore, as we did in this large study. So it was kind of a compromise between a precise inclusion criteria and sample size. I mean sample size in the sense of a number of data sets. But I fully understand your point that you were a bit surprised that RF was, well, significantly better. I think it's related to the choice of the data sets. And I cannot describe the data sets in a few sentences. I mean, there are 250 data sets, so we didn't look at each of them in detail, you know. Our focus was more on having a very large collection, which is, of course, well, an inconvenience, both advantage and inconvenience, depending how you see the problem.
Yes, no, thanks for commenting. And I think you carefully phrased that in the paper. So, but this issue of which studies to include, how broad you can go, they are very different, as you say, in the medical field, maybe different from other fields. Maybe if there's time later, we can also speculate on what are these other fields where prediction issues come up. But medicine is a big field, and but again, also within medicine, it will be heterogeneous in terms of well, the sample sizes, number of predictors,
yeah, sure.
Also, yeah, say how hard the problem is. So for diagnostic research, sometimes we have better prediction models than for far away, difficult to predict outcomes. So it may all these things may impact on this average, these pooled results, as you say. Yeah. So it's again it links nicely with my subsequent issue is on this merging of different. What can we combine? And what can we learn them, or do we have a next level of interpretation issues? Actually, as you also say, well, this average of 0.04, what does it relate to? It's a mixture of studies that was underlying that.
In a way, it's similar to precision medicine or treatment effects that are different for patients depending on their characteristics. Here, it's a similar aspect that. Yes. You have data sets characteristics that obviously affect the method's performances, and so inclusion criteria are very important.
So I see no more questions now in the chat.
Yeah, so probably more come up later on, but let me just continue with the second part then of presentation. Yes, still works. So this was the first part, and now let's move on to this data and analyses. So data sharing is of course a key issue in open science. Let me give you some reflections. So the first quote I put here is something that I still remember. I was in a plane and I was reading this magazine for the I don't know, not KLM, but was a cheaper carrier, I think American Airlines or so. Anyway, you don't get what you deserve, you get what you negotiate. And I think that was kind of the quote that I thought, this is actually important. I'm flying to New York to talk to people, to contribute data to a project. So it's not what I deserve, that I would just say, science deserves this. No, I would negotiate it. Well, so I flew to New York, I present plans, I listened carefully to them. It was also very interesting to learn. But of course, you need to give them something. So the traditional thing to give is a co-authorship. Right, that's how this works. So, and this project was, I think, overall was a success in the sense that we combined data from various groups. So New York was the first group to join, but eventually I had access to individual patient data from 6 study groups. This was published in '95, so it was relatively early to this kind of study. So why would you do this? Why 6 study groups? Well, because the numbers were relatively small if you had only one study group. It was a relatively rare disease. So here I had my own study, which was published, I actually showed it was prognosis after resection. So people had surgery, what are their outcomes after that? And here I already had 3 centers, so Leiden, Rotterdam, and Amsterdam participated, but only 85 patients. So to make a prediction model would of course be very stable and reliable. So I thought there would be benefits from other people who also published on that. This is New York and some other groups. So in total, we had 544 patients in this study. So that is beneficial, I think, from a statistical point of view. Higher numbers, you can do better modeling. But then there may be heterogeneity, the issue that Anne Laure actually also addressed already a bit on the study, the databases, and also between patients, here between studies. So heterogeneity was actually ignored. I was still very young, I say now, but I think it was not okay to just ignore it. So there are these 6 studies, but if you look at the results for the regression model, it had some characteristics here, but there's just odds ratios presented here with confidence intervals, but there's nothing on any between study difference, any between study heterogeneity. It was just said, okay, let's ignore it. So the good thing about this project was that it allowed for larger sample size in a relatively rare disease. So I think, yes, it was in a good journal because of this higher numbers. Well, the heterogeneity, it was not clear, it was just ignored. And it took substantial politics and efforts to get the data. That flying to people, really visiting them, that worked well. There was no specific sponsoring for that. It was kind of an extra effort in the PhD trajectory. But yeah, so this is how it worked in one example. Now I have another example for prostate cancer. It's a bigger disease, not testicular cancer was the first. This is prostate. a really big project, lots of funding, millions of dollars went into this. The GAP3 consortium, there are overall 20,000 men from 27 cohorts. And this nice map shows it. Were all uploaded. The data were uploaded in a central database. The database was by Philips Research in Eindhoven in the south of the Netherlands. Erasmus participated, and many, many other hospitals, US centers, also from Asia, all over the world. So really such a really major project. But then we looked more carefully, so maybe I was wiser now, look at variation between centers. So here are not all centers that participate, but many I think that at least have data to show, but then look at this difference. So the main interest is in progression, disease progression. These men are put on active surveillance. They can wait with active treatment, wait with surgery or radiation. So will progression occur? Well, the Vancouver study is only short follow-up. On the x-axis is time of follow-up. The red line is sometimes 30%. But then you go to South Korea. There's actually no progression happening, it seems. In Malmö, there's a lot. And here you can go to each of the centers. But these patterns, this is interesting. Memorial, I had visited that for testicular cancer. They don't have progression. It's really, there's a line here, but it's only, what is it, 7% or so. And there's a lot of anxiety, apparently, why people drop out. So this is the incidence of dropout by anxiety, but progression is not observed. Here, London, Europe, there's a lot of progressions. It goes to 100% in the end. Small numbers here. So really, really confusing. And so after all these efforts, I was actually quite, to bring the data together, I was rather disappointed to see this huge heterogeneity. So we looked here at variation between centers. The hazards were really low in some centers and really high in others. And we tried to adjust for covariates, so make these men more comparable, adjusted analyses, but actually it's very similar pattern. So it's not a lot of the heterogeneity that is explained by the observed covariates here. So heterogeneity, I think, is really the key issue of this example. So again, the data sharing allowed for larger sample size. Heterogeneity was studied now explicitly, but I put an exclamation mark. It's really, there was a lot of that. And again, a lot of politics and efforts were involved to get all these cohorts together. So that's my reflection on data sharing. But also moving on a bit to analyses. Odyssey project. I don't know, some people may have heard about that. It's a really important, big initiative, really open science. And it bridges this data sharing idea with analyses. I'll show some of that. So this is the newsletter they have, Odyssey, Observational Health, Data Sciences and Informatics. So very nice, classic, the myth of Odysseus, Odyssey, travel, observational data. So they have an official newsletter. Again, this nice map, but now other centers who all participate in the Odyssey project. So this official newsletter, they will provide updates, etc. And what they want, they have a really good ambition, meaningful evidence to impact both health and healthcare. So, well, evidence, that's important, of course, to have, and they try to get evidence from observational data, which is a challenge. So in this newsletter, they say, well, what did we do? We worked especially in COVID. So that's an opportunity for a lot of research, lots of things, initiatives, collaborative initiatives are happening. So they say, well, we did this COVID-19 study-a-thon, a hackathon, a data-thon, whatever ton. Yeah, they brought people together to work really for 4 days intensively. I participated in some of these webinar kind of calls where they showed ongoing projects, and it's all international, really, really fascinating. And this is a shining example, they say, of the power of collaboration. So it's really the open science spirit. They put papers that came forward from this initiative, so 5 studies on medRxiv. I think, Heidi, you also advertised that, or you mentioned it at least, right, as a where you can put a repository of preprints. And now they are looking for 2 more studies, and they're seeking data partners, people to participate. So I think it's really all in the spirit of open science. Very, very, in my mind, a really positive example of what people can do. There's one paper that I like to show that, say, illustrates the power of Odyssey, what they can do. So design implementation to generate, evaluate patient level prediction. So this is a prediction study based on this observational healthcare data. So how does the Odyssey network, the Odyssey project, get this project done? Well, the key thing is that they have a common data model. Common data model, in their case, the OMOP common data model, that enables the sharing of model development code. So the graph here shows this Odyssey network. So the people, the dots on the map, the people have, they have access, they have their own databases. So data 1 to data n, but they may be rather heterogeneous in their raw data structure. The data are locally, they are in different formats, different naming, etc. So the key step is here that this OMOP common data model translates these databases to a common data model. Here's model 1 to n. So this step makes that the data are accessible. They have a uniform definition of all the variables that are in. And then they can do things centrally, like, okay, I define a prediction question. What is the outcome? What's the time at risk for the populations that I want to look at? You extract the data. So with one, the script can work on 1, can work on 2, can work on whatever, as long as it's this framework, this formatting. Then you get labeled data, and you can do the predictions things like learning a model, evaluating a model within your own setting, so an internal validation. But also you can go from your model 1 to other data sets, so for external validation. So this whole structure allows internal and external validation of prediction studies. And that's all starts with this common data model, I think. That's key. What do they get out? Well, performance, they looked at different outcomes. They did a really multi-outcome study, so glaucoma, hemorrhage, acute MI, stroke, so all kinds of outcomes in 4 databases. So when I look at this, I see, okay, this is around 0.8 in the, again, this C statistic, area and ROC curve, discrimination measure, 0.8. And some other outcomes were a bit more difficult to predict, so 0.7 for other outcomes. But then this is all on the cross-validated performance, so in this database. And then if you look at other databases, I don't know the exact definition, but here the results are all a bit poorer. They're all 0.7 at most, 0.6. So this was apparently what I would think a data quality issue. That was also the question about related to methods versus data. I think the data are really important if there's not that much information. Well, here's a good score, but in general, it was harder to predict in these databases than in this or in Optum. This is a very big US-based claims database, I think. Question by Ulrich was also on calibration. So they did look at this. So as such, I think that's important that they not only looked at discrimination, but also at calibration of predictions. So I think it's overall a very nice example of how we can bridge this issue of how we share data and how we do analyses on these on the data set. And this example specifically on prediction, but they also look at treatment effects, medication effects, etc. So the idea is that you keep the data local and you run locally started. There's someone who programs centrally available analyses. So you bring the analyses to the data rather than the data to the centralized position. And the results from the analyses are, of course, shared. So you can then make this paper, as I showed, where you see the performance statistics and that sort of thing. So I think Odyssey is a very interesting open science idea. And then as a final point, go to the interpretation, because that is actually also in all the stuff that all the material that I showed. The challenge is really on this dealing with heterogeneity, I think. And that starts with study design. Are we looking at registries, observational studies? Are we looking at randomized controlled trials where we will use the data again? The selection of subjects may be quite different between studies. How do we measure the covariates? What are the definitions of blood pressure? How was it measured? All kinds of covariates may be measured in different ways. The outcome definition, That's for example, in cardiovascular disease, if you read the Framingham studies, they are often looking at very different, slightly, not very, but slightly different variants of the cardiovascular disease outcomes. And that's also in trials that we see that at MACE, major adverse cardiac events, they may be slightly different between studies. That impacts on the associations that we will observe of covariates with an outcome. So in the prediction context, these regression coefficients will be slightly different. And the overall outcome rates will also be different, as I showed for this prostate cancer example, where there were really large differences between studies. And then eventually what I care about, what's the performance of a model, calibration, discrimination, that will also be different between settings. So these are all elements, or probably more, where there's heterogeneity. And let me just illustrate one recent thing that we did about that. That was we thought about, well, how can we assess this heterogeneity if you have this relatively neat context of individual patient, individual participant data in a meta-analysis on prediction. So again, my favorite topic, it comes back again. How do you deal with that? And we worked with that with some colleagues from the Netherlands. So first thing we describe is, okay, we have the study, 15 cohorts, relatively nice sample size, 1,000 or several hundreds of patients, traumatic brain injury patients. There were 11 randomized control trials, 4 observational, so that's already a heterogeneous aspect. If you look at the case mix, so the studies are at the x-axis, 15 studies, the age distributions, well, the medians are actually quite different. Motor score, a strong prognostic factor, everything differs between studies. Well, you could say, well, okay, it's not a problem because I'm going to include that in my prediction models. But nevertheless, it's a starting point to show that these studies were really different from each other. And also, if you look here at 6-month outcome, that was the primary outcome in the study, differed substantially. If you look at the predictor effects, this is then a forest plot. So there are 15 studies here. If you look at the model intercept, so the average risk differs. The age effects, yeah, they do differ. Motor score, maybe in this visualization, they are rather consistent. But for all of these effect estimates, yes, they will differ by study. Now, as a prediction person, I'm really interested in how that impacts on the predictions that you would make. So one proposal we have here is this really very busy graph. It was apparently printed, but we try to compare predictions from one study with another. So you make a model in study 1, and we look at the predictions made in study 2 for the full cohort, so for all the 15 studies together. So they actually here there are 10,000 predictions shown. How do they correlate if you base prediction on study 1 or on study 2? So I enlarge this a bit. So if you go from study 1 and study 2, they seem to be very close to the 45-degree line and a very strong correlation. Don't know whether it's the best way to summarize, but very good correspondence, you might say, 45-degree line. And that's explainable because these are two variants of a randomized controlled trial, one run in Europe, one run in the United States. One US-based study. So these are really, they in design and protocol, they were really very similar. So also the model prediction, the predictions we get out, also very similar in this case. But if you go to other studies, so study 1, a model made there versus study 2, then you see that, yes, that is really slightly different. And do I do this right? Is it this one? Yeah, that's here. And if you go to study 2 and the study 3, again, we see these veins. So this is based on some categorical covariates in the model. There you see this pattern. But you see that the correspondence is less if you look at other studies. And some they were really different predictions. So this really shows heterogeneity at the prediction level, at the individual level. And if you look really at individuals, the impact of dealing with heterogeneity was illustrated here. So this is what I did in my 95 study. I said, well, there's no heterogeneity. There's some covariate. In this case, we look at age on the x-axis. Age is here. And then on the prediction. And then I would say, I am really certain what the prediction is. Because in this case, there are 10,000 patients in total. So I'm really sure what I can predict based on age. But if I allow for the between study variability in the random intercept, so between study variability, then my uncertainty is much bigger. So kind of prediction interval approach here, I can make the model a bit more flexible, allowing for differential effects of the prognostic index per patient, per study. Prognostic index heterogeneity, rank 1 model we call that. It's again a little bit bigger and fully stratified. So just say, okay, the model is made per study and the variability is even bigger. And so here at the end, a 70-year-old, you could say, well, it's around 20% to 60% is a probability. That's kind of the prediction interval here. So just to illustrate that, yes, heterogeneity is a key issue, I think. Well, that is actually then near the end, I think. How are we doing in time? Yeah. So the overall claim I'm still very strong on, that open science will make research better. And one example was this red cards example. We look at with multiple teams, the neutral comparisons, as we discussed, a meta-analysis. Meta-research is also a classic approach to get insight in, say, bigger questions, get the overall picture. I talked a bit about data sharing, and maybe you could question mark, is it old-fashioned? And really to try to upload data to a central place. Should we not go for this Odyssey variant, where we have the modern approach of bringing the analyses to the data? And I've seen that in other contexts. There are also hybrid approaches. But I think the old-fashioned just data sharing may not be really needed. But then the key issue is this heterogeneity, that there are differences between studies, between settings, and some we can identify. And so we have covariates, but some are just hidden and there are really a difficulty. So in my view, this open science research extends the discussions that we may have had already for many years on meta-analysis, on how to interpret overall results. And a parallel we can make here that I learned from others is if you look at Cochrane reviews, they are very critical on which randomized controlled trials to include in a review. They will be really discussing that for days with experts. Is this trial eligible for, is it appropriate to include it? And if you contrast that to, say, a big data approach, where you would just say, give me any data you have, and I will summarize it for you. And that is a contrast in culture that I think is still there and is even more clear when we go in the open science direction. So I think that is what I wanted to talk about this far, and I guess Heidi and others that we can take some questions and discussion now. And then I did prepare that what you showed here, some statements that we can to really get some more ferocious discussions and all objections on issues that come up in open science. But perhaps it's best to first stop here.
Thank you so much, Ewout, for this amazing talk. I would like to hand over now to Urs, who will lead the discussion.
Excellent.